Hey guys, tonight we go back further than almost any bedtime story ever dares to tread, back to a time when Earth itself was barely recognizable. The date is roughly 4,400,000 BCE, and if you could stand here in the middle of what will someday become the continents, you wouldn't last long enough to blink. Beneath your feet the ground is not really ground at all but an unsteady shell of cooling rock. Above your head, fire and stone still rain from the skies. The world is wrapped in choking clouds of vapor, sulfur and ash, glowing faintly orange as molten rivers cut across a surface still hotter than a pizza oven. The smell is acrid burnt minerals, volcanic smoke, metal sizzling in raw heat. You hear nothing but distant roars of impact, followed by silence, then another crash. You're on a planet being born in violence. And here's the cheeky truth, you probably won't survive this, unless your idea of a good time is swimming through lava and inhaling poisonous steam. But that's exactly why tonight's journey matters. We're going to explore how a place like this, fiery, hostile, boiling with chaos, eventually gave rise to the oceans that now cover more than 70% of Earth. Stick around to see how the impossible happened. If you're new here, hit subscribe for more sleepy deep time adventures on the strangest chapters of Earth's past. Drop your location and local time in the comments. Imagine explaining where you are now to someone living 4.4 billion years ago. Sleep well knowing that even the first oceans had to fight to exist. Tonight we float back to where it all began. The first thing you notice as you step forward is that the Earth's surface is not steady. It shifts and cracks, groaning like cooling glass. Vast plains of molten rock stretch in every direction, shimmering under a haze of toxic clouds. The planet, once completely liquid fire, has begun to form its first skin. The molten mantle has cooled just enough in some regions that basaltic crust solidifies on top, brittle and thin like a scab. You stand on one of these early crustal rafts, feeling it tremble beneath you as magma seeps through fissures, reminding you that below lies a restless interior, still hotter than 2000 degrees Celsius. Asteroids and comets slam into this fragile surface every few minutes, each one striking with the power of 1,000 hydrogen bombs. The impacts gouge vast craters, rip up any new crust, and throw molten debris back into the atmosphere. Some of the projectiles are iron-rich, and when they explode, liquid metal rains down, spattering the rocks with glittering molten beads. Others carry silicates, carbon compounds and water locked in ice crystals, delivery trucks from the outer solar system that unknowingly bring the seeds of oceans to come. The glow in the skies is constant. Sometimes it's the dull red of erupting volcanoes, other times the white-hot flash of an incoming impact. The air is unbreathable, thick with carbon dioxide, sulfur dioxide, and methane. Clouds of steam roil upward, then mix with ash. Lightning flickers inside these turbulent clouds, striking down on molten plains with crackling fury. The soundscape is never still, the hiss of vapor, the deep belly rumbles of the planet's crust adjusting under its own weight, the sharp concussion of impact. And yet, amid this chaos, something remarkable is happening. Slowly, stubbornly, the molten seas are cooling. Every time an asteroid punctures the surface, heat escapes more rapidly. Every night, if we can call it that, the glow dims a little more. Tiny crystals of solid rock form in the molten soup, float upward, and lock together, hardening into a primitive crust. The planet is forming its first protective shell, uneven, fragile, and constantly recycled by new impacts, but a shell nonetheless. You imagine crouching down, pressing your hand to this early crust. It feels scorching, but there's a texture, ridges, bubbles, glassy streaks, as if the whole planet were one giant volcanic glass workshop. Here, feldspar and pyroxene minerals are beginning to differentiate from the melt. Heavy elements like iron and nickel have already sunk deep into the core, generating a magnetic field that pulses invisibly around you. That magnetic bubble, though weak, will someday shield the planet from solar winds, helping to keep water molecules from being stripped away into space. Even at this embryonic stage, Earth is setting the table for oceans. Of course, don't get too comfortable. That shell beneath your feet is not permanent. Over here a fissure opens, spilling molten basalt like a broken artery. Over there an impact the size of a small continent rips the crust wide open, erasing everything in a glowing splash. Earth is in a constant cycle of destruction and renewal. Crust forms, is obliterated, and forms again, over and over, like a planet that can't quite make up its mind. But here's the critical point. Each cycle traps a little more stability than the last. Every new crustal plate that solidifies lasts slightly longer before being melted away. The cooling intervals stretch from days to years, to centuries. Slowly, Earth transitions from a fully molten hellscape into a world with patchwork surfaces, giant islands of rock floating on a magma sea. It's not paradise, it's not even survivable, but compared to the inferno of 4.5 billion years ago, this is progress. If you squint through the choking haze, you can picture the outlines of what will someday be continents, not actual land masses yet, just stony rafts floating on a deep, restless mantle. They grind and crash into each other, fracture, and remelt. Imagine playing a game of Tetris, where every piece you place immediately bursts into flames. That's continental formation in the Hadean Eon. The sky above reflects the chaos below. Dense with particles and volcanic gases, it glows copper and crimson, filtering the young sun's rays into a permanent twilight. Sometimes the atmosphere tears open during impacts, venting plumes of steam into space before closing again. But each venting episode is followed by more volcanic outgassing, geysers of steam and carbon dioxide shooting into the air from thousands of fissures at once, constantly replenishing the sky's choking density. And here's the punchline: for all the violence and destruction, this is the gentle beginning of the story of water. That steam billowing out of every vent is water vapor, endless reserves of it, stored in the molten mantle. Every time the crust cracks open, more vapor escapes upward, thickening the atmosphere with the promise of rain. The asteroids striking down deliver even more, frozen cargo that vaporizes instantly in the heat, but lingers in the sky. The Earth is still on fire, but above the inferno the ingredients for oceans are gathering. You take another step across the uneven crust, hearing it pop and crack like glass cooling too quickly. Somewhere beneath your feet, convection currents churn, dragging chunks of solidified crust downward to be remelted, recycling minerals back into the mantle. This restless interior ensures that Earth will never settle into a static rock like the Moon. It will remain dynamic, always shifting, always resurfacing itself, and that dynamism is exactly what will allow it to host oceans, atmospheres, and eventually life. So tonight, in this first step of the journey, you stand on a fragile crust above a still molten heart, under a sky heavy with poison and promise. The seas do not yet exist, but their ingredients are here, trapped in vapor, hidden in ice, bubbling in magma. The Earth is cooling, just enough, just slowly enough to let them gather, and as fragile as it looks, this is the first step toward a planet of blue. The crust you're standing on is just the beginning. Beneath your feet, an extraordinary act of planetary housekeeping is underway, the sorting of minerals by weight. Heavy ones sink, light ones rise. This process, simple in principle, transforms Earth into a layered world, and lays the foundation for what we'll someday call continents. The first crust isn't uniform. Instead, it's a chaotic mix of basalts, volcanic glasses, and primitive rocks, with exotic names like komatiite, ultra-hot lava that only formed in these earliest eras. When it erupted, it flowed faster than modern lava rivers, rushing like torrents of liquid fire across the cooling surface. You imagine the heat rolling off it, shimmering waves that distort your vision, the stench of sulfur so strong it prickles the back of your throat. The cooling crust fractures again and again. Blocks of basalt crash into each other, some sinking back into the magma, others piling up to form rafts. These rafts don't yet resemble continents, but they're the prototypes. The moment molten rock solidifies into feldspar or quartz, it's a step toward buoyancy, lighter than the mantle beneath. Each eruption builds little islands of solid rock, short-lived but significant, floating on an ocean of magma, like foamy crusts on boiling soup. Picture yourself climbing onto one of these rafts. The surface is rough, jagged, newly crystallized. Tiny crystals of plagioclase sparkle in the faint red light of the smothered sun. The rock is hot enough to make the soles of your feet ache if you stood too long, but not so hot that it melts instantly. You crouch down and trace a hand across the texture, glassy in one place, bubbly in another, fractured everywhere. Each bubble was once a gas pocket, carbon dioxide or water vapor trying to escape from molten stone. Even though you're not breathing, let's imagine you could. The air above this crust is poison, but it's also heavy with water vapor, nitrogen, carbon dioxide, and sulfur compounds. When you look upward, you don't see a blue sky, you see an ochre haze, thick with volcanic ash and dust, trapping the heat below like the worst greenhouse imaginable. The sun is nothing but a faint disk, occasionally flashing when a gap opens in the smog. Every now and then you feel the planet convulse. Deep below, convection cells, massive rivers of molten rock, are shifting the crust around. Some of the heavier minerals, like olivine and pyroxene, are tugged downward. Lighter minerals float upward, creating streaks of silica-rich rocks that will one day become the seeds of continental plates. You're witnessing the earliest differentiation of Earth's surface, an invisible sorting hat working patiently beneath the chaos. But don't get too confident. Over the horizon, a fiery glow suddenly brightens. A massive impactor, an asteroid, dozens of kilometers across, slams into the proto-crust. The ground beneath you shakes so violently that standing upright is impossible. Within seconds, shockwaves ripple outward, fractures race across the ground and molten fountains erupt around you. In the aftermath, half of the crust here is obliterated, melted back into the mantle. And yet, strangely, this destruction is productive. Every impact stirs the mantle, dredging up new material, adding new chemistry to the surface. Some impacts deliver rare metals, others deliver frozen water, still others simply churn the cauldron of the planet. The crust reforms quickly, magma cools into basalt again, patching the scar. Each cycle makes the surface a little thicker, a little stronger, a little more resistant to being wiped clean. Imagine looking down at one of these new rock sheets. Embedded inside are zircons, tiny crystals that billions of years later, geologists will discover in places like Jack Hills, Australia. Those zircons are among the oldest surviving solids on Earth, survivors of this very era. Holding one in your hand would be like holding the memory of the first crust. They are proof that even amid bombardment and fire, minerals stabilized long enough to last almost forever. So here you are, standing at the dawn of geology. Beneath the chaos, Earth is quietly becoming structured. A metallic core spins below, generating a weak magnetic field. Above it lies the dense mantle, hot but churning, and above that mantle floats the crust, fragile rafts of basalt and cometite, forming and reforming in endless cycles. Every tremor you feel, every volcanic hiss you hear, every fiery glow on the horizon is part of this planetary ballet of destruction and renewal. And you realize something, though it looks catastrophic, this is exactly the process that makes the Earth special. Without crust, there can be no oceans. Without oceans, there can be no life. Right now it's just fractured rafts on a boiling planet, but the blueprint of continents is being drawn, and you're watching it, second by second, as minerals find their place and the skin of Earth thickens ever so slightly. The ground beneath you has barely settled when another booming roar echoes across the horizon. The skies split open again, and this time, it isn't just one or two small rocks raining down. It's an entire cosmic artillery barrage. You are living through the period geologists call the Late Heavy Bombardment, and Earth is the unlucky target in a cosmic shooting gallery. The solar system at this time is still young and messy. The big planets Jupiter, Saturn, Uranus, Neptune are tugging and shoving asteroids around like bullies in a schoolyard. Cometary fragments ricochet inward from the outer regions, spiraling toward the sun and smashing into anything in their path. Earth, still glowing in patches with molten scars, takes a disproportionate share of hits. At times it seems like every few hours the planet is slammed by something the size of a mountain. Stand here long enough, and you'll see it, a streak of fire as an object tears through the dense atmosphere, heating to white-hot brilliance before impact. Then the world explodes in shock. A plume of vaporized rock soars upward, blasting into the upper atmosphere, raining molten droplets across thousands of kilometers. The sound hits you a moment later, deafening, concussive, like 1,000 thunderclaps rolled into one. The ground heaves, your ears ring, your chest rattles. You are not watching destruction from a distance, you are standing inside it. Every crater gouged into the surface is instantly a laboratory. When rock is pulverized and melted, it releases minerals. Impact heat vaporizes ice carried by comets, dumping water vapor into the air. Iron and nickel scatter across the proto-crust. Shockwaves fracture newly hardened basalts, creating networks of cracks that later will channel water deep into the ground. Even in chaos, the ingredients of stability are being arranged. It's worth pausing here because for modern humans, oceans are calm, familiar, and blue, but in this era, every droplet of future ocean water is delivered in violence. Picture it, a frozen comet from the Kuiper Belt slams into Earth, releasing its cargo of ice. For a moment, the ice flashes into steam, expanding into the dense, hot air. Most of it rises high and lingers as vapor, thickening the already soupy skies. Some escapes into space, stripped away by the energy of the blast, but much of it remains, trapped by Earth's growing gravity and thickening atmosphere. Each comet delivers a little more, each asteroid adds minerals, salts and elements that will someday dissolve in seawater. Step carefully now. Around you the landscape is a ruin of craters, smoldering lava pools, and jagged ridges. Some craters are so large they collapse inward, forming giant basins. These will one day become natural catchments, perfect places for water to pool when the atmosphere cools enough to allow rain. Right now though they glow red and orange, filled with molten basalt. Smoke and ash rise like curtains over their rims, choking the horizon. The bombardment is relentless, but it does something crucial. It mixes the planet. Without it, Earth might have cooled into a uniform shell. With it, material is constantly stirred, crust is shattered and remade, and volatile compounds are continually added to the atmosphere. Think of it as a brutal planetary chef, stirring the ingredients of a future ocean with asteroids as spoons. You crouch and pick up a piece of molten glass, just hurled here by an impact. It's still glowing faintly. When it cools, it will be a tektite, a glassy bead created by impacts, flung across the globe. Billions of years later, geologists will still find these little messengers of the bombardment in ancient rocks. Each one is a postcard from this era, signed in fire. Of course it isn't just Earth suffering. Look up toward the moon. Its surface, too, is pockmarked again and again. Each crater you see being carved into its face is permanent, because unlike Earth, the moon lacks tectonics to recycle its crust. Billions of years later, astronauts will walk across that frozen record of impacts, but down here on Earth, the scars are erased, almost as quickly as they form, melted, recycled, smoothed over by lava and heat. That's why Earth's earliest history is nearly invisible today. Its surface never stayed still long enough to keep the scars. Yet, as violent as it seems, this bombardment is running on a clock. Over tens of millions of years, the number of impacts will decrease, the orbits of the big planets will settle, the barrage will slow, and Earth will finally get a chance to breathe. By then though, the planet will have absorbed an enormous inheritance, not just rocks, but the very atoms of its oceans, oxygen, hydrogen, salts, carbon, all delivered in explosive packages. The funny part, you might think of this as a nightmare, but Earth needed it. Without those comets and asteroids, there wouldn't be enough water to fill the oceans. Every glass of water you've ever sipped, every wave that's ever rolled onto a beach, every drop that's ever rained from the sky, each one has an ancestry in this bombardment. You could almost raise a toast to the chaos. Cheers to the asteroid that gave you your morning coffee. For now though, don't linger too long. Another bright streak is crossing the sky, bigger than the last. You'd best crouch low and brace yourself. The first oceans of Earth are coming, but they're arriving on the back of fire and fury. The bombardment slows, but it doesn't end. You look out across a world still shuddering with fire, yet something different is beginning to assert itself. Among the molten plains and fractured basins, there's a new rhythm, delivery after delivery of water from the skies. Every comet that streaks through the thick haze brings with it the same crucial ingredient: ice. Picture one, a frozen mass the size of a city, careening toward Earth at tens of kilometers per second. As it slams into the atmosphere, friction peels its surface away in a blinding arc of fire. By the time it collides with the crust, it explodes in a blast, so bright the entire horizon glows. For a moment, water trapped inside the comet is freed, hydrogen and oxygen molecules scattering, fusing, vaporizing into dense steam. The ground shakes but the sky thickens. Every collision leaves behind another invisible layer of potential ocean. Now multiply that by millions. The sheer number of comets and water-bearing asteroids that pepper the planet during this time is staggering. Some come from the outer asteroid belt, their interiors rich in hydrated minerals, rocks with water bound inside their crystal structures. Others hail from far colder realms, icy nomads driven inward by gravitational nudges from the giant planets. They break apart in showers, littering the Earth with droplets of frozen water that immediately boil into vapor, then linger in the heavy skies. And yet the story of Earth's oceans is not written in comets alone. Look around you, countless volcanoes line the horizon, fountains of molten rock spewing skyward. With each eruption, enormous plumes of gas billow into the air. These gases include carbon dioxide, sulfur dioxide, nitrogen, and crucially, water vapor. Vast amounts of it, released from the mantle where it had been locked since the planet's earliest formation. You watch as geysers of steam gush upward from fissures, swirling into the sky. The air grows denser, wetter, almost soupy. Lighting crackles through the vapor, flashing purple against the orange haze. The smell is pungent: sulfur, ash, scorched minerals, and beneath it, the faint dampness of steam settling on hot rock. Even though it is far too hot for liquid water to survive on the surface yet, the atmosphere is already loaded with it. It's an astonishing thought, the oceans that will someday lap against beaches, cradle coral reefs, and host the first life forms are already here, hanging invisibly above you. They are not yet rivers or seas, but clouds and vapor. In fact, if you could part the haze and see Earth from space right now, it would appear swaddled in a thick, shimmering veil. Not blue, not green, but coppery and silver, glowing faintly as the sun strikes its endless storm decks. Meanwhile, down below, the crust plays its part. Imagine droplets of rain, tiny, superheated, boiling before they can even strike the ground, falling on black basalt. Each droplet instantly sizzles away, leaving behind a faint mark of mineral residue. Over time, as this cycle repeats, minerals leach from the basalt, dissolving into the steaming runoff. These elements, sodium, calcium, magnesium, will eventually define the chemistry of seawater. Right now they're just beginning to trickle into the mix. There's a delicate balance at work. Too much heat, and water vapor would simply escape into space, blasted away by solar radiation. Too little volcanic outgassing, and Earth might remain dry, its atmosphere too thin to hold on to moisture. But thanks to Earth's magnetic field, faint but real, the solar wind is deflected just enough to keep much of the vapor bound here. The gravity is strong enough to hold on to the heavier molecules, while the blanket of carbon dioxide traps heat, ensuring the planet doesn't freeze. Every eruption, every comet strike, every outgassing vent is contributing to a single outcome, a planet growing wetter by the hour. You sit down on a jagged rock, the heat radiating through you, and close your eyes. You imagine what this must look like in slow motion, vapor rising from magma seas, volcanic steam joining it, icy comets adding still more, layer by layer, droplet by droplet. The invisible ocean grows overhead, and when the cooling reaches a tipping point, all that vapor will finally fall as rain. It's tempting to think of oceans as calm, peaceful, eternal, but here in 4.4 billion BCE, they are anything but inevitable. They are fragile, dependent on a perfect convergence of violence and chemistry. If Earth had been smaller, like Mars, its atmosphere would have slipped away long ago. If it had been larger, like Jupiter, hydrogen would dominate and water as we know it wouldn't exist. But Earth is just right, a Goldilocks planet, where the collisions of ice, the belching of volcanoes, and the pull of gravity align to create seas. So tonight, as the bombardment still rages but begins to ease, you tilt your head back and breathe in the sulfurous steam. You're breathing the ghost of future oceans, suspended above you in thick clouds. The surface may be hellfire, but the sky is a promise. Oceans are on their way, and soon they will pour down in torrents, so relentless they will reshape the entire planet. For now though, it's vapor and thunder, fire and ash. Earth is gathering its waters, one comet at a time, one volcanic sigh at a time, waiting for the moment when gravity, chemistry and cooling all agree. Let it rain. The atmosphere is swollen now, heavy with steam, carbon dioxide and the haze of volcanic gases. You tilt your head upward and feel the air pressing down thicker than anything breathable. The sky is not blue, not even close. It is a dense cauldron of shifting grays, copper streaks and flickering lightning bolts that scrawl across the firmament like furious handwriting. Earth is smothered beneath a blanket of greenhouse gases, and oddly enough, this suffocating cloak is the reason the future oceans will not freeze before they even begin. Imagine, standing on a raw basalt plain, your feet inches from a glowing fissure where magma oozes like molten tar. The air stings your skin. Every inhale would choke you with sulfur dioxide and carbon monoxide, but your attention isn't on breathing, it's on what's happening above. Towering storm clouds, taller than anything you've seen in the modern world, pile on top of each other until they scrape the upper atmosphere. They are heavy with moisture, their bellies sagging with vapor, but they cannot yet release their burden. The ground is too hot, the crust still radiating the heat of a planet fresh from formation. Any droplet that dares fall is annihilated in an instant, hissing back into steam before it reaches the ground. But cooling is inexorable. With every passing millennium, Earth loses a little more of its molten fever. Volcanic eruptions are still constant, but the crust is thickening, forming plates of basalt that last longer before they are recycled into magma. Between impacts, the surface manages to stabilize just enough to cool slightly. It's still a hellscape, but a cooler hell than before, and that makes all the difference. Now picture the atmosphere as a giant distillation chamber. Water vapor condenses high in the skies, forming colossal droplets that coalesce into clouds. For ages, they hover, growing denser, darker, more swollen. Finally, as the cooling crosses a critical threshold, they can no longer hold back. Gravity wins. The first real raindrops fall, not boiling away instantly, but splattering across the rock in sizzling defiance. One droplet becomes 10, 10 become a downpour, and then it begins, the first torrential rains in Earth's history. It doesn't just rain for an hour, or a day, it rains for millennia. The skies unleash their burden in a flood so relentless, it feels like the planet is dissolving beneath it. Every square kilometer of rock is hammered by raindrops the size of marbles. Streams cascade across the surface, rushing into cracks and fractures, carrying with them the first dissolved minerals. Steam rises from every impact, fogging the land in an endless haze, until the entire world looks like it is wrapped in boiling mist. Stand here for even a moment, and you are drenched, not with refreshing cool water but with searing hot rain that stings the skin. Your body feels it as both relief and punishment, the atmosphere cooling but still burning hot. Rivers form in an instant, carving channels into the black basalt. Pools gather in low basins, only to be boiled away when lava surges through fissures. Yet the rains continue. They do not stop. For thousands upon thousands of years the storm is endless. The soundscape is overwhelming, rain hammering the crust like drumfire, thunder rumbling through the heavy air, volcanoes roaring in the distance. It is a planet being washed, scoured by water that has waited hundreds of millions of years to fall. Each drop carries with it not just moisture, but the future of life itself. They mix with minerals in the rock, pulling sodium, magnesium, calcium, and potassium into solution. Every puddle becomes a test tube, every rushing stream a chemical lab. And something else begins to happen. The rain is not falling on a smooth planet. Remember those craters gouged by bombardment? They are waiting now, vast depressions, scattered across the crust, their rims jagged, their interiors deep. As rainwater pours down, these craters fill. Some boil off quickly, but others are large enough to hold on to their cargo. Pools form, small at first, then larger. Some merge into vast basins. You are witnessing the very first outlines of ocean. The air begins to clear, ever so slightly. Each downpour strips particles from the sky, scrubbing soot, ash and dust downward. Slowly, through the copper haze, the sun flickers a little brighter. It is still a dim glow compared to the modern sky, but it is the first hint of light filtering through storms that have lasted for ages. It is almost comic to think. You probably imagined the birth of oceans as a gentle drizzle filling empty valleys. Instead, it is a deluge, so violent it would make Noah's flood look like a summer shower. Entire landscapes are reshaped in days. Basalt plains are shattered by erosion. Molten flows are quenched by cascades of water, hissing and exploding into fountains of steam. Lava lakes are capped with brittle crusts as rain hardens their surface, leaving behind cracked shells where rivers cut through. If you close your eyes and listen carefully, you can almost hear the ocean's first heartbeat. It is not yet calm, not yet permanent, but the planet is taking its first true bath. Water, endless and unstoppable, is here to stay. The atmosphere, once nothing but fire and suffocating gas, is now part of a cycle. Evaporation, condensation, rainfall, the hydrologic cycle has begun. Earth is no longer just a rock, it is becoming a water world. And all around you the rain still falls. For thousands of years, the deluge doesn't relent. The future oceans are carving their space, drop by drop, storm by storm. You stand soaked, steaming in the mist, realizing that this endless rain is the single most important event in the planet's history. From here on, Earth will never be dry again. The rains have been falling for so long that the ground is no longer recognizable. Where once there were jagged plains of basalt and fresh craters, now there are vast, pooling basins brimming with water. The bombardment that once scarred the surface has unintentionally created the perfect topography for oceans. Deep depressions carved by impacts, lowlands formed where the crust sagged, valleys where molten flows once spread like rivers of fire. You walk across a ridge of still cooling rock and look down into one of these new basins. At first it was just a crater filled with steaming water, but centuries of rain have transformed it into a colossal inland sea. Mist hangs above its surface, glowing faintly under the filtered sunlight. Steam rises in pillars where fresh lava meets the water's edge, hissing into clouds. The air is thick, damp and metallic, tinged with the scent of dissolved minerals. This is not the ocean you know. It is hot, acidic, dense, with chemicals leached from stone, but it is an ocean in the making. Across the planet, these basins link together, floods carve channels from one to the next, uniting isolated lakes into sprawling seas. Rivers form where constant rainwater cuts down through ridges, carrying sediment and dissolved salts along with it. You can hear the rush everywhere, an unending symphony of moving water. For the first time in history, Earth has a hydrological landscape, flowing currents, pooling lakes, roaring waterfalls plunging into molten basins. Yet nothing is stable. The crust beneath your feet groans and shifts constantly. Entire regions of seabed crack open without warning, swallowing the waters back into the mantle. Other regions rise, pushed upward by surges of magma, tipping lakes out like spilled bowls. Oceans form, vanish and form again, in a cycle of destruction that lasts thousands of years. And still, the rains fall, relentless, ensuring that even when water is lost to the mantle, more takes its place. You crouch at the edge of a basin and dip a hand into the water. It's scalding hot, near boiling in places, but it clings to the land with persistence. Droplets bead on your fingers, carrying the faint sting of acid. In that water, dissolved from the black basalt beneath, are the first salts of Earth's oceans. Sodium, calcium, magnesium, iron. Each mineral will help define the chemical signature of seawater. Later, these same minerals will shape how life can exist, feeding reactions, balancing cells, becoming essential nutrients for creatures not yet imagined. Look farther out, the basin stretches toward the horizon, choppy with winds that whip the surface into waves. At its center, geysers of steam shoot upward where submerged fissures vent heat from the mantle. These submarine hot springs bubble violently, stirring the water, creating constant motion. This turbulence prevents the water from settling into layers. It's all churned together, a restless chemical soup. And Earth is not finished filling these basins. Overhead, the deluge continues. Clouds darker than night tower over the planet, their undersides flickering with ceaseless lightning. Rain pours in sheets, hammering the proto-oceans with a sound like drums rolling across the entire globe. Every drop carries with it not just moisture, but energy, kinetic force that churns the waters, sparks that trigger reactions when lightning strikes. You realize you are watching not just the formation of oceans, but the first experiments in chemistry that will someday lead to life. Now imagine stepping back and seeing Earth from orbit. For the first time in its history, the planet is not just a glowing molten orb. It is streaked with dark reflective patches, proto-oceans catching the dim sunlight, shimmering beneath layers of cloud. They are not yet vast blue expanses, but they are unmistakably seas. Earth has begun its transformation into the blue planet. Of course, the planet doesn't give you a calm honeymoon. Over there, at the far edge of the horizon, an eruption tears open a fissure miles wide. Lava surges outward, crashing into a growing sea with explosive violence. The clash of fire and water sends steam plumes higher than mountains. Entire basins are boiled dry in hours, leaving behind charred plains of black rock. And yet, the rains refill them. Within weeks, water flows back, pooling deeper than before. This cycle, eruption, evaporation, refill, repeats endlessly, but each round leaves the seas more permanent. Something extraordinary happens as the basins stabilize. The constant rain, combined with mineral leaching, begins to change the water's chemistry. It's no longer pure condensation, it's a complex brew. Dissolved carbon dioxide makes it acidic, dissolved salts make it briny, dissolved metals make it faintly toxic. But it is precisely this complexity that makes it powerful. The first oceans are not lifeless wastelands, they are cauldrons of possibility, simmering with the ingredients of biochemistry. You sit at the shoreline, your feet in the steaming surf, and listen to the waves crash against basalt. You can almost imagine the centuries sliding past, one after another, as the rains feed the seas, as the basins deepen, as water grows ever more abundant. Drop by drop, basin by basin, the world is being reshaped. And tonight, as you close your eyes against the hiss of rain and the rumble of magma, you realize something simple but staggering. Earth has crossed the threshold. The first stable oceans have begun to take shape, fragile yet undeniable, shimmering across the battered crust. They are hot, acidic, restless, but they are here to stay. By now the rains have carved a planet of rivers and steaming basins, but what's happening above your head is just as important. The atmosphere is swelling, thickening with every eruption, every comet strike, every droplet of vapor that refuses to escape into space. The sky has become a permanent ceiling of storm, and the gases within it are shaping the destiny of the oceans. Look around, volcanoes still dominate the horizon, hundreds, maybe thousands, erupting at once. spewing fountains of magma and towering plumes of smoke. Each eruption coughs out carbon dioxide, methane, ammonia, nitrogen and of course, enormous amounts of water vapor. Together they form a dense, multi-layered shroud that locks the planet in suffocating warmth. This greenhouse world is not gentle. Sunlight struggles to break through, casting only a dim, rust-colored glow. At the same time, the gases trap heat from the young sun, preventing Earth from freezing despite the star being fainter than it will be in the future. In fact, here's a cosmic joke. The sun was about 30% dimmer at this time, faint enough that Earth should have been a frozen snowball, and yet, thanks to the over-enthusiastic belching of volcanoes, the planet is hot enough to keep its newborn seas in liquid form. Take a step forward, and you feel the ground tremble. Fissures hiss steam like giant kettles, feeding the sky's heavy clouds. You hold out your hand. Raindrops still fall, warmer than bath water, stinging slightly from their acidity. Each drop carries carbonic acid, formed as carbon dioxide dissolves into the vapor before condensing. When those drops strike rock, they leach even more minerals, accelerating the transformation of bare crust into seawater chemistry. Now imagine Earth as an enormous pressure cooker. The atmosphere is dense enough that when water condenses, it doesn't escape immediately. It cycles, vapor rises, condenses, falls as rain, and evaporates again when it hits hot crust. This churn repeats endlessly, a planetary sauna that ensures water molecules keep circulating rather than vanishing into space. With every cycle, more gases are scrubbed from the air and dissolved into the seas. And oh, those seas, they are growing. Craters and basins that once held steaming puddles are now filling into permanent reservoirs. You watch as two such basins connect. A waterfall plunges over a jagged ridge, linking one proto-ocean to another. The sound is deafening, a roar of white noise that echoes across miles. Spray rises in clouds mixing with volcanic ash. Lighting flashes through the mist, striking the surface and sending ripples of energy across the water. You can almost feel the chemistry shift under your feet. Electrical sparks catalyzing reactions in a stew of minerals and carbon compounds. Meanwhile, the sky is gradually sorting itself. The heaviest particles of ash and dust are pulled down by rain, clearing the atmosphere bit by bit. What remains are the gases, the thick haze of CO2 and methane, layered with nitrogen. The world is still suffocating, still toxic, but less opaque than before. Occasionally a weak shaft of sunlight pierces through, glinting on the water's surface. For the first time, the oceans shimmer with something like light. And yet, the greenhouse blanket is crucial. Without it, Earth's early oceans would have frozen solid under the faint young sun. Without it, hydrogen atoms from water molecules would have escaped to space, leaving the planet dry. Instead, the atmosphere holds them down, trapping heat, creating a humid cradle for seas to grow. The irony, the same gases that would suffocate you now are the reason life will one day exist. You walk along a shoreline, waves slapping against basalt ridges, foam hissing as it eats away at rock. The water is no longer just a film or puddle, it is deep, restless, heavy with dissolved minerals. Sodium and chloride ions mix here, the earliest hints of the saltiness that will one day define the ocean. Every wave is a chemistry experiment, every bubble a microlab. And there's motion, constant motion. Winds tear across the seas, stirring waves into chaos. Volcanic heat bubbles up from below, driving currents that swirl and churn. The moon, newly formed and much closer than today, pulls at the waters with powerful tides. Imagine standing at the edge as the sea rises dozens of meters, then retreats, slamming against rock with a force that grinds it into sand. These tides keep the waters restless, mixing their contents thoroughly, ensuring no basin stagnates. Take a moment to laugh here. You might have pictured Earth's first oceans as calm pools forming under a cooling sky. Instead, they're more like the world's worst hot tub, boiling, acidic, bubbling with volcanic gases, stirred by colossal tides, and sparked by lightning every few minutes. Yet this chaotic cocktail is exactly what's needed. Complexity thrives in turbulence. The rains continue, but the atmosphere is stabilizing. The planet is shifting from a place of raw bombardment into one of cycles, rain, rivers, evaporation, tides, currents. This isn't just geology anymore. This is the first climate system. Earth has gone from molten rock to a water planet wrapped in storms, with chemistry dancing in every drop. You exhale, if you could breathe this air, and realize that for the first time, Earth doesn't just have seas, it has a system that will keep them alive. The greenhouse atmosphere, for all its violence, is no curse. It's a shield, and beneath it, the oceans are claiming their place, not as fleeting puddles, but as the permanent heart of the blue planet. You stand at the edge of a steaming shoreline and realize something remarkable. The rain hasn't stopped in what feels like forever, and now those basins are overflowing into one another. Earth's first oceans are no longer scattered puddles. They are merging, swelling into vast expanses that stretch across the surface like liquid continents. Everywhere you look, the landscape is being redrawn. Valleys carved by ceaseless downpour channel rivers into lowlands, and those rivers pour into great bowls gouged by ancient impacts. As the bowls fill, they breach their rocky rims, spilling over with catastrophic force into neighboring basins. The result is a cascading network of water, rivers linking lakes, lakes joining seas, seas rising into proto-oceans. You are witnessing the hydrosphere locking into place. Step closer to the water and listen. Waves crash not gently but violently against the basalt coast, chewing at the rock. Each impact breaks fragments loose, grinding them into sediment. Streams sweep that sediment into the sea where it settles into muddy layers at the bottom. For the first time, Earth is storing its geological history in sediments that will, billions of years later, fossilize into rocks. It's the beginning of the rock record, the diary of the planet. The chemistry of these newborn seas is changing by the hour. Rain continues to leach sodium, calcium, and magnesium out of basalt. Volcanic gases pour carbon dioxide into the water, where it dissolves into carbonic acid. Hydrogen sulfide bubbles up from vents, giving the air a rotten egg sting. Lightning flashes across the surface, splitting molecules, fusing others. The seas are not sterile, they are an unruly broth, a primordial soup in the making. Look farther out, toward the horizon. The water isn't calm, it heaves and swells. The moon, still orbiting much closer to Earth than today, exerts immense tidal pull. Imagine tides hundreds of times more powerful than modern ones. Entire shorelines vanish under surges of water, then reappear as seas retreat. Currents churn ceaselessly, mixing the chemistry of the oceans from surface to depth. This restlessness ensures no drop of water remains static. Everything is blended, circulated, agitated. If you dare step into the water, though you probably shouldn't, you'd find it scalding hot near vents and fissures, cooler but still warm farther away. Minerals coat your skin, leaving a salty film. The water tastes metallic, briny, sour with acid. It's a far cry from the crisp oceans you know, and yet there is something mesmerizing in its complexity. Here is a medium dense enough, rich enough to support reactions beyond mere geology. These seas are chemical factories waiting for the right sparks. Storms still dominate the skies. Even though the bombardment has eased, the atmosphere remains turbulent. You look up and see clouds stacked in layers, thunderheads flashing with purple lightning, rain falling in curtains. The roar is endless, the hammering of water, the hiss of steam, the crack of thunder. But beneath the chaos is continuity. For the first time, the rains are not filling empty basins. They are maintaining oceans, keeping them topped, feeding them as they evaporate and cycle back. Now step back, way back, in your imagination. Picture Earth from orbit. The planet, once a molten ember, now wears patches of shimmering water. They reflect faint light from the young sun, glinting like mirrors through the haze. Earth is still not the deep sapphire orb we know, but the transition is undeniable. Oceans are spreading, claiming territory, locking themselves into the very fabric of the planet's surface. It's tempting to call this stability, but don't be fooled. Beneath the seas, the crust is restless. Volcanoes continue to erupt underwater, creating hydrothermal vents. These vents spew superheated fluids rich in iron, sulfur and other minerals, forming black, smoky plumes that billow upward like chimneys. Around them, minerals precipitate, coating the seafloor with metallic crusts. Each vent is an alien world in itself, extreme in heat and pressure, but brimming with chemical gradients, perfect energy sources for whatever chemistry might come next. You kneel at the shoreline and dip your fingers into the churning surf. The water is no longer fleeting. It is no longer just boiling mist. It is permanent, dense, insistent. It is the ocean, and it has finally claimed its place on Earth. You can almost sense its permanence. No eruption, no storm, no comet can erase it completely now. The oceans are here to stay, sculpting shorelines, filling basins, defining climate. And yet, the thought creeps in, this ocean, still so young, is far from peaceful. It is restless, acidic, heavy with minerals, but in that restlessness lies potential. The foundations of life will not come from calm waters, but from these turbulent, mineral-rich seas. Tonight, As you stand by the roaring waves of Earth's first oceans, you realize you're standing not just at the edge of water, but at the edge of possibility. The seas are no longer timid puddles, they are vast, surging bodies of water stretching across the planet, and they are not quiet. These are not the tranquil blue oceans of postcards. These are chaotic, steaming cauldrons, constantly stirred by heat, tides, and impacts that have not completely ceased. If you were hoping for a calm swim, well, you'd last about 2 seconds before being boiled, crushed, or dissolved. Stand at the shoreline. The surf crashes violently against jagged basalt cliffs, sending sprays of acidic foam into the air. Every wave bites at the rock, prying loose fragments, grinding them into gravel, then into sand. Sediment rivers into the sea, clouding the water in swirls of gray and black. At the base of the cliffs, steaming plumes rise where fresh lava oozes into the sea, turning water into vapor with a deafening hiss. It smells of sulfur, iron and salt, sharp enough to sting your nose even through the thick, choking air. The seas themselves are restless. Tides rise and fall dramatically, pulled by the moon's still close embrace. Imagine standing here and watching the ocean retreat miles from the coast, exposing steaming flats of black rock. Hours later the water roars back, surging upward in a flood that climbs cliff faces and batters them until chunks collapse into the surf. These aren't gentle tides, they're planetary heartbeats, massive and violent, keeping the waters in constant motion. And then there's the heat. Beneath the waves, the crust is thin, fractured, and alive with volcanic activity. Hydrothermal vents, some spouting at hundreds of degrees Celsius, line the seafloor. They gush superheated fluids, saturated with minerals, iron, manganese, sulfur, even trace metals like copper and zinc. As these hot fluids mix with cooler seawater, they precipitate into clouds of black smoke, coating the ocean floor with strange chimneys and metallic crusts. Imagine entire undersea ranges glowing faintly from heat, the water shimmering as if alive. Currents driven by this geothermal engine swirl ceaselessly, moving heat and minerals across the oceans. Warm upwellings rise, cooler waters sink, storms above stir it all even more. Nothing in these oceans is ever still, and that's good. Stillness would mean stagnation, but turbulence means opportunity. Every churn mixes minerals, gases and heat, creating chemical gradients that make reactions possible. Lightning still plays its part. You glance skyward and watch as bolts crackle through the atmosphere, striking the surface of the ocean with blinding flashes. Each strike splits molecules apart, forging new ones in the chaos. Ammonia, methane and water vapor are reassembled into complex carbon molecules. It is chemistry on a planetary scale happening in every storm, every wave, every droplet. The atmosphere itself is heavy with greenhouse gases. It is mostly carbon dioxide, with nitrogen as a background filler, methane adding its own warming punch, and hydrogen sulfide giving it the delightful scent of rotten eggs. If you could breathe it, it would be your last breath. Yet paradoxically, this toxic cloak is protecting the oceans. It keeps heat from escaping into space, shielding the seas from freezing under the faint young sun. Without it, these first oceans would vanish as quickly as they formed. Now take a step back, way back in your imagination, and picture the whole Earth from orbit. The molten scars are fewer, the bombardments rarer, and there, covering lowlands and craters, shimmering beneath the haze, are the first true oceans. They are dark, murky, restless, nothing like the sapphire seas of today, but they are undeniable. Earth has crossed the threshold from fire world to water world. There is something eerie about them too. No life swims here, no fish leap from the waves, no birds cry overhead. The silence is broken only by thunder, waves and eruptions, and yet if you stand long enough, you feel the weight of what's coming. These oceans are not just features of the landscape, they are the laboratories where life will be born. Every tide that churns minerals, every lightning strike that cracks carbon bonds, every vent that spews superheated water is preparing the stage. You crouch at the edge of a tidal pool, steam curling around you. The water bubbles faintly from underlying heat. You scoop a handful and watch it drip between your fingers. It's heavy with salts, metallic tasting, bitter, but inside this liquid, possibilities are endless. Here, in these chemical soups, the foundations of biology will soon take their first, clumsy steps. For now though, the oceans are wild, uninhabited, and merciless. They crash, they boil, they churn, and they whisper nothing of what's to come. But you know the secret. This chaos is no accident. It is the exact crucible that will, in time, give birth to life. You lean closer to the shoreline, watching how these new oceans chew at the crust itself. The rains may have carved rivers, but now the seas are sculptors. Every wave is a chisel, every tide is a hammer. Slowly but relentlessly, the water reacts with the raw basalt beneath it, unlocking new chemistry with each surge. The black volcanic rock is not inert. When acidic rainwater and mineral-rich seawater hit hot basalt, the surface fizzes, releasing ions into the ocean. Sodium, calcium, potassium, all dissolve out of the rock, enriching the water with salts. Silica leaches into solution, altering the chemistry further. Even iron oxidizes here, staining the shallows a faint reddish hue. You scoop a handful of this water and watch the droplets glisten. This isn't just wet, it's a chemical broth, infused with the very building blocks that will someday nourish cells. On the seafloor, the story is just as busy. Hydrothermal vents, those roaring undersea geysers, are performing constant alchemy. Superheated fluids erupt from fissures, mixing with cooler seawater, precipitating minerals that settle around the vents like smoke made solid. Sulfides of iron and copper form chimneys meters tall, black smokers belching chemical plumes into the ocean. These vents are laboratories, creating stark differences in temperature and chemistry from one side of a vent to the other. If you lean in close, ignoring for a moment that you'd be cooked alive, you could almost see the gradients shimmering, hot to cold, acidic to less acidic, mineral-rich to mineral-poor, and in chemistry, gradients mean potential. It's not just the vents. Entire ridges of the seafloor are still splitting apart as magma rises, creating long cracks where seawater gushes in, flashes to steam, and re-emerges enriched with minerals. This constant interaction between water and rock means the oceans are never chemically quiet. They are dynamic systems, their composition changing hour by hour. The air above adds its own contributions. Carbon dioxide dissolves into seawater in vast amounts, forming carbonic acid. Ammonia and methane, belched from volcanoes, rain down into the water, sparking with lightning as they fall. The seas absorb nitrogen as well, not yet in the stable form plants will one day use, but still an essential ingredient swirling into the mix. And oxygen, none of that yet, not free oxygen. Anyway, these are anoxic oceans, dense and suffocating by modern standards. They shimmer dark, metallic, almost oily, reflecting the copper glow of the stormy skies. But here's the paradox. Even in their toxicity, they are nurturing. Without oxygen, fragile molecules can form and linger without being immediately destroyed by oxidation. Without clarity, the thick chemistry of these waters is free to stew. Every tide that slams against rock, every storm that lashes the seas, every lightning bolt that strikes the surface, is driving the chemistry further. You walk along a headland where cliffs plunge into frothing surf. The rock is jagged, glassy, still brittle from recent solidification. Waves smash into it, eroding fragments into pebbles, pebbles into sand, sand into mud. Those sediments tumble into the sea, layering the seafloor with minerals. Already, Earth has begun its first sedimentary cycle: erosion, transport, deposition, and inside those layers, the chemistry of the oceans is recorded, grain by grain. Billions of years later, humans will find these rocks and trace the story back to this very time. The tides too are carving their mark, because the moon still looms close. Its gravitational pull creates tidal surges beyond anything you can picture from modern coasts. Entire stretches of shoreline vanish under walls of water, only to be revealed again hours later. Pools form in the intertidal zone, heating in the sun, evaporating into brine. These pools concentrate minerals to levels far higher than the open ocean, creating miniature chemical cauldrons along every coast. Imagine standing over one, watching it bubble and thicken like soup left too long on a stove. And then, crack, another lightning bolt slams into the water's surface, splitting molecules, generating hydrogen cyanide, formaldehyde, simple sugars, amino acid precursors. These are not just exotic compounds from a chemistry set, they are the letters of life's alphabet, scattered liberally across the seas. The ocean is not lifeless, it is pregnant with possibility. The atmosphere clears just slightly, enough for a dim shaft of sunlight to penetrate. It glints off the restless waves, illuminating the churning surf. For a brief moment, the ocean looks almost familiar, rippling water reflecting light. But beneath the surface, the chemistry is alien, experimental, unstable. You're watching a planet mid-experiment, brewing the recipe that will someday lead to biology. You crouch at the edge of a tide pool, stick your hand into the briny water, and feel its warmth. Pull your hand out, and lick your palm, if you dared, and you'd taste something recognizable: salt. This is the first moment when Earth's oceans truly begin to resemble their modern selves. They are salty, restless, and permanent, and though no life stirs here yet, the water itself is becoming the canvas upon which life's story will be painted. Earth has finally given itself oceans worthy of the name. Now the stage is set for something even greater. The oceans now stretch like restless mirrors across the planet, and for the first time they are not fleeting pools but permanent seas. They move, they churn, they crash, but they endure. As you stand at the edge of this newly waterlogged world, you begin to notice a rhythm emerging, something beyond storms and rainfall. The oceans are learning how to behave. From the coast, you watch the tides roll in with terrifying force. The moon, still much closer than in your time, pulls enormous bulges of water across the surface. Imagine entire shorelines disappearing under a surge, then re-emerging hours later, only to be devoured again. Some tidal shifts would dwarf modern tsunamis. This is not the gentle lapping of waves, but planetary scale heaving, as if the whole ocean is inhaling and exhaling. You step back and look inland. Rivers, swollen with relentless rain, carve deeper valleys into the crust. Sediment is carried in torrents to the sea, where it settles in layers on the seafloor. Each layer adds to the growing oryx of the planet's history. Thicker muds, chemical precipitates, metallic deposits forming in strange bands. Already the geology of Earth is writing its first detailed record, though no one will read it for billions of years. Beneath the waves, the oceans are far from quiet. Submarine volcanoes roar, spewing fountains of lava into the water. Each eruption is instantly quenched, solidifying into pillow-shaped rocks that litter the seafloor. Between eruptions, hydrothermal vents gush superheated, mineral-rich fluids. These vents line cracks and ridges, their plumes curling upward like smoke. Minerals precipitate in clouds, forming chimneys of iron and sulfur that rise like alien towers from the deep. If you could wander among them, the water would shimmer with heat, glowing faintly from the energy of the Earth's mantle escaping below. Currents sweep the seas in vast loops. Warm waters rise near vents and fissures, spread outward, then sink again as they cool. Tides reinforce the motion, ensuring the oceans are never stagnant. The entire hydrosphere is in motion, a planetary washing machine, turning over and over, mixing minerals, gases and heat, and in that constant mixing lies a hidden gift. Every corner of the ocean is exposed to new chemical possibilities. The atmosphere above has changed too. Volcanic gases are still pouring out, but the rains have scrubbed much of the soot and ash from the skies. The result is a murky but thinning haze. For the first time you catch sight of the sun more clearly, a pale disk, glowing weakly through copper clouds. Its light reflects off the restless water, scattering across waves in glints of silver. The planet no longer looks like a furnace cloaked in smoke, it looks just barely like a water world. And those waters are evolving. With each rainfall, each volcanic belch, each leaching reaction with rock, the chemistry of the seas grows richer. Ammonia and methane dissolve into them, providing nitrogen and carbon. Hydrogen sulfide mixes in from vents, feeding gradients of energy. Iron saturates the water, giving it a dark, metallic sheen. Salt accumulates drop by drop, giving the oceans their distinct taste. What you're staring at is not just water, it's a simmering soup of possibilities, a planet-sized experiment where the ingredients of life swirl freely. Now consider what happens when lightning cracks down from the sky. Each bolt splits molecules in the air, and at the surface, recombining them into new forms. Simple organics, like amino acids, flicker into existence in scattered patches. They don't yet cluster or self-replicate, but they persist, floating like whispers in the surf. It's as though the oceans are rehearsing for a play not yet ready to be performed. You crouch at the shoreline again, watching the tide retreat. Pools remain in hollows, steaming under the heat. As the water evaporates, minerals concentrate to brines thicker than seawater. In those brines, chemistry accelerates. Molecules bump into one another more often, binding, breaking, rebinding. These tidal pools are not just coastal puddles, they are miniature laboratories, amplifying the experiments already happening across the ocean. From space, Earth is unrecognizable from its molten youth. The crust is darker now, streaked with wetness. Lowlands are flooded, basins glitter with permanent water. Clouds still swirl above, but breaks reveal a surface shimmering with reflections. For the first time in cosmic history, the Earth looks alive, even though life itself has not yet begun. It is a blue world in the making. And though no creature yet stirs, the conditions are now firmly established. The oceans are stable enough to endure, restless enough to stir chemistry, rich enough to feed future complexity. What was once a molten ember in space has become something entirely new, a water planet, breathing storms, surging tides, and preparing its seas for the first sparks of life. The oceans are no longer scattered across the planet like disconnected pools. They have merged into immense, planet-spanning bodies that now dominate Earth's surface. You are standing on the edge of a water world, and though the seas are far from peaceful, they are undeniably permanent. The crust itself groans under their weight, bending, flexing, reshaping the very geography of the young Earth. From your vantage point on a rocky rise, you watch a panorama, unlike anything on modern Earth. Below lies an endless expanse of dark, churning water, its surface steaming in places where hot fissures lie just below. The horizon is blurred by haze, broken only by volcanic arcs and ridges poking above the sea like jagged islands. Those islands are fleeting, some collapse back into the waves within centuries, others are swallowed by lava floods, but for now they stand like stepping stones scattered across a restless ocean. The water itself is nothing like the clean, sparkling blue you might expect. Instead it is opaque and metallic, stained by dissolved iron and other minerals leached from the crust. The seas look dark green, brown, even black in places, their colors shifting with chemistry and depth. Each wave carries the sting of acid, the brine of salt, the tang of metals. They smell of sulfur and ash, a cocktail of volcanic exhaust that lingers over the surface. If you dared to taste them, they would burn your tongue and coat your throat with bitterness. Step down to the shore, waves smash into the rock, eroding it, grain by grain. Every impact pries sodium and magnesium loose, feeding the oceans with the salts that will define them forever. Over time, chloride ions accumulate as well, balancing the mix. This is the beginning of the salinity of seawater. The ocean is becoming chemically distinct, not just a pool of condensed rainwater but a true marine system. And the seas are alive with energy, not biological yet but geological and chemical. Hydrothermal vents still spew superheated fluids at the bottom, their plumes curling into black clouds that drift with the currents. Tidal forces slam water against coastlines, then drag it back with crushing weight. Winds, born from violent storms above, whip the surface into frothing waves. Everywhere you look, the ocean is moving, restless, incapable of stillness. You notice something fascinating. In shallow regions along the coast, evaporation begins to concentrate minerals. Pools left behind at low tide grow brinier as the sun weakly filters through the haze, heating them enough for water to vanish into vapor. These concentrated pools are rich in salts and metals, tiny, hypersilene worlds distinct from the open sea. They act like miniature chemical crucibles, amplifying reactions, storing molecules that would be too diluted in the vast ocean. You crouch beside one, watch bubbles rise, smell the sour tang of sulfur. This too is part of the preparation. Above, the atmosphere has thinned slightly, no longer clogged with constant soot. It is still dense, still toxic, still greenhouse heavy, but shafts of sunlight now pierce through. The sun gleams on the surface, catching waves in flashes of gold. The Earth, seen from orbit, is transforming, no longer a smoking ember, but a hazy wet orb flecked with glimmers of reflected light. It looks fragile, shimmering, almost alive. Tides continue their work. Because the moon remains close, gravitational pulls are enormous. Coastlines are ripped apart by surging waters, then exposed to scouring winds when the seas retreat. Pools concentrate and evaporate, minerals accumulate. You realize that without this tidal chaos, much of the chemistry that will later matter simply couldn't occur. The moon, that silent companion, is already shaping the destiny of life by keeping the seas in motion. And here's the cheeky thought: if you were dropped here today, you'd curse the environment, acid seas, choking air, endless storms. But in truth, you're standing at one of the greatest sweet spots in cosmic history. Too much heat, and all this water would have boiled away. Too little atmosphere, and it would have escaped into space. Instead, Earth is perfectly balanced, just stable enough, just dynamic enough to hold on to its oceans and stir them into complexity. You close your eyes and listen. Waves roar, thunder rolls across the horizon, a vent hisses in the distance. Lightning flashes, splitting the sky, striking the surface of the sea with a sizzling crack. For a moment, the water glows faintly, disturbed by raw energy. The oceans shimmer, restless and alive with possibility. The planet has its seas now, not shallow puddles, not boiling mists, but deep, enduring oceans. And though they are harsh, though they are wild, they are here to stay. The blueprint of the modern Earth is written in their tides. The oceans no longer feel like intruders on a hostile world. They have become the dominant feature of the planet. From horizon to horizon, water stretches across vast basins, rolling restlessly under storm-heavy skies. This is not yet the blue jewel of Earth as you know it, but the transformation is undeniable. You are now standing on a water world. The seas are dense, saturated with minerals, sodium and chloride, dissolved from basalt and concentrated by endless rainfall, are steadily establishing seawater's salty character. Magnesium, calcium, potassium, and silica swirl alongside them, creating a complex soup of ions. If you cupped a handful of ocean water now, it would sting your eyes, burn your throat and taste metallic, but chemically, it is evolving towards something familiar. These are the very foundations of the chemistry that will one day nurture life. And everywhere the oceans are alive with motion. Strong winds rake the surface into whitecaps, roaring storms whip the water into chaos, and the moon's gravitational tug continues to drive extreme tides. Whole shorelines are swallowed and exposed again within hours. Rivers, swollen with rain, pour sediment and minerals into the seas, adding to their complexity. Nothing is still, nothing is quiet. The world is endlessly churned, endlessly mixed. Beneath the waves, another drama unfolds. The crust is thin, cracked, restless. Water seeps into fissures, meets molten rock, and re-emerges as superheated plumes. Hydrothermal vents line ridges and basins, their jets of black, mineral-laden water pouring into the ocean depths. Around them, chimney-like structures of sulfides build up, growing taller with every eruption. These vents spew not just heat but chemistry, iron, sulfur, manganese and trace elements, like copper and zinc. In their plumes, steep gradients of heat and acidity form, creating natural laboratories scattered across the seafloor. If you dive deeper, and somehow survive, you'd see the oceans layered like a living gradient. Near the vents, the water shimmers with heat, boiling hot in some places. Farther away, it cools into the upper layers, though cool is still warmer than modern seas. Everywhere, minerals swirl. The oceans are dark, murky, tinged with hues of green and black from dissolved metals. These are anoxic waters, without free oxygen, thick and alien compared to the breathable seas you know. The skies above, though clearing slightly, remain turbulent. Lighting still lances down through the heavy clouds, striking the seas with energy that splits molecules apart. Ammonia, methane and carbon dioxide are transformed into new compounds. Simple organics form spontaneously, tiny molecules like amino acids, nucleobase precursors and simple sugars. Fleeting, fragile but real, they scatter across the surface waters carried by currents, concentrated in tidal pools, evaporated and recondensed. Chemistry is no longer random, it is directed by cycles, rhythms, and repetition. Along the coasts, the tidal pools become crucibles. When the tide rushes in, it fills them with fresh seawater. When it recedes, the pools are left behind to evaporate, concentrating their contents. Minerals precipitate along the edges in crusty rings. Organic molecules, created by storms or vents, are trapped, condensed, recombined. Lightning and ultraviolet light from the weakly filtered sun provide further sparks. Each cycle leaves the pools richer than before. If you crouch beside one and watch closely, you can almost imagine the molecules colliding, sticking, building into larger chains. Not life, not yet, but a rehearsal for it. Meanwhile, the planet itself is settling into a new identity. The heavy bombardment has slowed, impacts still occur but less often, and fewer of them are catastrophic. The crust thickens, stabilizes, the seas deepen, spreading across the surface, seeping into fractures, blanketing basins. With every passing millennium, the Earth looks less like a scarred battlefield and more like a world in balance. Oceans below, atmosphere above, geology and chemistry in constant conversation. From space, the difference is staggering. Earth now glows with the sheen of water, its surface reflecting sunlight through the haze. It is still wrapped in storm clouds, still shadowed by volcanic exhalations, but its seas are unmistakable. Compared to the dry, barren neighbors Mars and Venus, Earth looks like an anomaly, a shimmering, stormy, restless blue-gray orb. And you realize something extraordinary. The planet is no longer just cooling, it is cycling. Oceans evaporate, condense, fall again as rain. Currents stir the seas, tides churn them, vents inject them with new material. The planet is not static, it is dynamic, a system of constant flux. That dynamism is exactly what makes it fertile ground for what will come. So tonight, As you sit by the roaring surf, watching lightning split the sky and vents hiss across the seafloor, you understand that Earth has crossed another threshold. It is not just a planet with ocean, it is a planet of chemistry in motion, a planet rehearsing the lines of a play that life will soon take up. The oceans are now the planet's permanent companions. They no longer flash into steam at every eruption, nor vanish entirely with each catastrophe. They endure, shaping Earth's identity. For the first time, the seas and the skies are working in tandem, exchanging heat, gases and water in cycles that will define the climate system for billions of years. Stand on the coast for a moment and feel it, the rhythm of the tides, the ceaseless roar of surf, the crash of waves against raw basalt cliffs. The ocean breathes now, rain falls, rivers feed it, tides churn it, storms stir it, and evaporation carries water back into the clouds. This closed loop, the hydrologic cycle, is fully alive. Earth has graduated from being a planet of random eruptions and impacts to being a planet with systems. The atmosphere above is thick, but it is stabilizing. Carbon dioxide still dominates, locking the planet into a greenhouse state, but the endless torrents of rain are gradually scrubbing some gases into the ocean. Nitrogen accumulates as a background gas, becoming the second major component of the air. Methane adds to the greenhouse effect, while hydrogen sulfide still taints the winds with its pungent odor, and oxygen, none to breathe yet. These are anoxic skies, a dense blanket of storm clouds and smog, streaked with lightning, hazy under the dim sun. But stability doesn't mean peace. Volcanoes still roar across the seafloor, and their hydrothermal vents continue to spew heat and minerals. Each vent is a crucible of extremes, scorching water on one side, cooler ocean on the other. Between them lies a sharp boundary, an energy gradient begging to be exploited. You watch clouds of black smoke rise, curling into the murky water. Minerals precipitate into strange towers, growing upward until they collapse, then rebuilding. The seafloor is a landscape of chimneys and ridges, glowing faintly with heat. The oceans themselves churn with complexity. Dissolved salts are reaching equilibrium, locking seawater into its distinctive salty profile. Iron saturates the seas, giving them a metallic sheen. In shallow pools, evaporation drives chemistry to extremes, concentrating minerals and organic molecules alike. You crouch by one of these pools, its water thick, almost syrupy. Lighting cracks overhead, and you imagine molecules inside colliding, sticking, forming longer chains. They don't yet organize into life, but they are flirting with the possibility. Sunlight, weak but present, also plays its role. Ultraviolet radiation penetrates the haze in brief flashes, striking the surface waters. It splits molecules, creates radicals, sparks reactions. Combined with lightning and geothermal heat, these bursts of energy are relentless. Everywhere on Earth, in the seas, the tides, the vents, the skies, molecules are being forged, destroyed, and reforged. The planet is running endless chemical experiments, over and over across every environment it has. Look again from orbit. The Earth has transformed, no longer just a smoldering rock, no longer just steaming pools. It now gleams faintly beneath a veil of storm. Oceans stretch across basins, reflecting what little sunlight reaches them. Cloud bands circle the planet, fed by evaporation and rainfall. This is no longer the fiery infant of 4.5 billion years ago. It is a world with climate, a world with seas, a world on the cusp of biology. And here's the cheeky thought: you're standing on a planet that looks uninhabitable by your standards. Acidic seas, suffocating skies, constant storms, yet compared to what came before, this is practically paradise. The Earth has cooled enough to hold liquid water indefinitely. Its atmosphere is thick enough to protect that water. Its cycles are established. The oceans are no longer temporary guests, they are residents. Sit back, close your eyes, and listen. The crash of surf, the hiss of vents, the rumble of distant eruptions, the low drone of thunder. That symphony will never truly stop. But within it patterns have emerged. The chaos has organized into cycles, and within those cycles, chemistry is edging toward complexity. Earth is no longer just a ball of fire wrapped in poison. It is a living system, not with organisms yet, but with rhythms, stability, and permanence. Tonight, as waves wash over basalt and storms flash overhead, you can feel it. The blueprint for life is etched into this ocean world. The seas are ready. The stage is set. The next act will not be geology, but biology. The oceans now command the world with authority. What began as fleeting pools has become a global hydrosphere, and their influence reaches everywhere, into the rocks, into the air, into the very heartbeat of the planet. They are not merely a feature of Earth, they define Earth. Stand at a high ridge overlooking a vast basin. Before you stretches an endless expanse of dark water, waves heaving under storm-heavy skies. The horizon blurs into mist, broken only by volcanic islands that rise and fall as lava builds them up, then collapses them back into the sea. From here you see the oceans as they truly are, not passive, not quiet, but forces that shape everything. The chemistry within them grows richer every century. Minerals leach from basalt, salts accumulate, and gases dissolve. Carbon dioxide enters the seas in vast amounts, making them acidic, while nitrogen collects quietly, laying the groundwork for future biology. Hydrothermal vents continue to inject metals and sulfides, creating oases of chemical richness at the seafloor. The oceans are no longer just water, they are a chemical engine, churning and mixing endlessly. Look closely at the coastlines. Tides, still monstrous, thanks to the moon's nearness, drag seawater far inland, then retreat, carving valleys and leaving tide pools behind. These pools are miniature laboratories. Water evaporates, concentrating salts, organic molecules, sparked into existence by lightning or sunlight, linger and recombine. You crouch by one, the brine so thick it shimmers like oil. With each cycle of flooding and evaporation, molecules grow more complex. They don't yet replicate, but they experiment, endlessly. From the depths, geothermal energy rises relentlessly. Vents gush black smoke, their chimneys forming towers of mineral deposits. Each plume mixes violently with seawater, creating steep gradients of temperature and acidity. Chemistry thrives at these boundaries, an eternal negotiation between hot and cold, acidic and neutral, rich and poor. It is here in these violent contrasts that the first whispers of proto-biological processes may one day find footing. The skies, too, have shifted. Ash and soot no longer cloak the heavens as thickly as before. The clouds are still dense, the air still suffocating, but sunlight now filters through in fractured beams. Ultraviolet light reaches the surface in bursts, energizing molecules in the shallows. Each photon becomes a spark, splitting bonds, forging new ones. Above, lightning continues to crackle across storm decks, raining down energy into the seas. Earth has become a laboratory powered by storms, tides, heat and sunlight, all at once. From space, the Earth is finally unmistakable, a water planet. Clouds swirl across its surface in bands and spirals, reflecting sunlight in brilliant flashes. Oceans cover most of the visible world, shimmering dark and metallic under the copper haze. Compared to its barren neighbors Mars and Venus, Earth is already unique. It is not just rocky, not just wet, it is dynamic, restless and fertile. You can sense the permanence now. The oceans will not vanish. They will grow deeper, more stable, more powerful. With time, they will regulate the planet's temperature, sculpt its crust, and carve its landscapes. They will absorb gases, scrub the skies, and carry minerals. Already, they have turned Earth from a furnace into something gentler, still dangerous, still toxic, but sustainable. And in this permanence lies a secret. Life does not emerge from stillness. It requires turbulence, gradients, cycles. The oceans are not peaceful, but they are endlessly stirring, endlessly mixing. They are restless enough to keep chemistry alive, yet stable enough to endure for billions of years. It is a paradox. Chaos creates stability. You crouch again at the shoreline, the waves hiss and retreat, leaving foam that sparkles faintly in the dim light. Each bubble is a tiny chemical world, fleeting, fragile, but carrying molecules that may one day become the scaffolding of biology. It feels almost absurd. You are staring at lifeless seas, yet they are brimming with the possibility of everything: forests, reefs, whales, people. All of it begins here, in this mineral-rich brine. So tonight, as thunder rolls and tides crash, you know the truth. The oceans are no longer an experiment. They are a system, a permanent part of Earth's identity. And soon, very soon, they will do more than carve rocks and trap gases. They will give birth. By now, the oceans have taken full command of Earth's surface. They stretch across basins, fill valleys, cover craters, and link together in a restless network of tides, currents, and storms. You are standing on a planet that is no longer molten chaos, no longer a battlefield of comets and lava, but a true water world. Look outward across the horizon. Waves surge in endless motion, their surfaces reflecting what little sunlight filters through the storm-laden skies. The water is still dark, metallic, laced with minerals, but it is deep, stable, and enduring. The continents as you know them don't exist yet, only volcanic ridges, Small craggy islands and temporary arcs of rock poke through the sea like jagged teeth. These are fleeting, swallowed by the ocean as quickly as they rise, but they are harbingers of the continents that will someday take root. Beneath the surface, the seafloor is alive with heat. Hydrothermal vents gush plumes of scalding water, building mineral chimneys that tower like strange skyscrapers in the depths. Each vent is an engine of chemical gradients, hot against cold, acidic against neutral, mineral-rich against mineral-poor. These contrasts drive reactions that, molecule by molecule, are weaving complexity into the oceans. Black smokers pour iron and sulfides into the water, coating the seabed in mineral crusts. White smokers release alkaline fluids, rich in carbonates, forming vents that fizz like submerged champagne springs. Together they lace the oceans with opportunity. The chemistry of the seas has matured. They are no longer simply condensed vapor. They are saline, mineral-saturated, and endlessly churned. Sodium and chloride dominate, defining seawater's taste. Calcium and magnesium balance the mix. Iron stains the water dark. Carbon dioxide dissolves into the seas in vast amounts, making them acidic, yet simultaneously scrubbing it from the skies and stabilizing the atmosphere. The oceans are buffering the planet, regulating its climate, locking Earth into a system that can last. And here's the marvel: though no life stirs here yet, the stage is ready. Lightning still splits the sky, raining sparks of energy into the water. Ultraviolet sunlight still penetrates in bursts, energizing molecules at the surface. Tides still churn the shallows, creating pools where evaporation concentrates chemistry. Every corner of the hydrosphere is a laboratory, running billions of chemical experiments simultaneously. Simple organic molecules flicker into existence, fragile but persistent. They scatter in the surf, linger in tide pools, swirl near vents. They are not alive, but they are the whispers of life, the alphabet waiting to be arranged into words. From space, Earth gleams. Storms swirl in bands across its surface. Vast oceans reflect dim light. Volcanic arcs trace fiery scars through the haze. The planet is no longer a furnace, no longer a barren rock. It is a shimmering orb of water and storm, a world with stability, cycles, and the restless seas that will cradle the first living chemistry. Compared to its neighbors, dry Mars, boiling Venus, Earth is already unique, already the outlier, already the planet of oceans. And so you sit at the edge of this restless surf, listening to the symphony, waves crashing, vents hissing, thunder rolling in the distance. The world feels empty, but you know better. The emptiness is deceptive. It is a